Give me the same position.
Yeah.
Like all the other people have already signed up.
Yeah.
Because they probably already have.
Or like they actually would like need it a lot more if you're like drinking by us.
I was like, I wish I knew. I'm irritated.
Hopefully it works out.
Yeah.
Yeah, I don't know if I should do that or no.
So you're thinking of using in the 233 as well?
Yeah, for sure.
What you sent it for last?
130.
It's
I have to
130.
like refresh. I have to watch some of my apps because I don't have I was like, I literally went back to this match because I had like the 9:45, so I was like, oh, I was done before because I didn't know what to do.
Yeah. I like schedule.
Is it the border? I think it's border. I should.
Yeah, and then you sort of like, you sort of the classic.
All right, so on Friday, we basically started going over glycolysis, right? So we started here kind of on the left. And then you see there our first molecule that we care about is going to be that glucose. As you go forward, that glucose is a 6-carbon chain. Right? And then you're going to cut it in half. You're going to make 2 chains of 3. And that's when we're doing our jump from our glucose to our pyruvate. Last Friday, I was trying to always focus on the chemical, and then I was looking at kind of the ATP production. But for today's class, we're really going to focus on trying to go this thing over the top. Right? So we're really going to focus on what's going on with those electrons. So in the first case, you see that from that jump, your glucose gets broken in the cytoplasm. You make your 2 pyruvate. We're putting in, you go out from the system 2 NADHs. Right? So there, each one of those NADHs is basically carrying 2 electrons. Those are high energy electrons. They have a lot of potential energy. That then has to get into the mitochondria, and it's trying to get, as it's going through this double, like the double phospholipid bilayers, it ends up like transferring the energy. So sometimes it can transfer the energy to another NADH, at which point you've kept the same amount of charge. If it sends the energy to an FADH2, in that case, FADH2 is a little bit weaker. So sometimes when we're giving you these values of what's the end product, this is the thing that's really going to mess with us up here. Depending on whether we can get the high power, from high power to high power, or high power to this low power, we'll input whether we have NADH, we can get 28. We have FADH, it's going to bring us down to 26. All right, so let me do my simple drawing so I can keep trying to flip that. All right, so we're saying glucose. This is your 6-carbon. This is going to get to our pyruvate. We have 2 3-carbon chains, right? This one, 2 NADHs have already been recovered, right? Once we start oxidizing that pyruvate, we're going to turn it into our acetyl-CoA. At this point, you have 2 carbon chains. And one of your waste products here is leaving, is the CO2. As we're going through this process, again, we're putting out more energy from this reaction, and we're getting ourselves 2 more NADHs, so more electrons are coming in, right? We take out some more. After that, our acetyl-CoAs are gonna go into the citric acid cycle. And when we go through the citric acid cycle, we're gonna end up using up these last 2 carbons, we're gonna split them up. And then here the product's gonna be, of course, our CO2, and you're gonna make 2 of them. Right? For every one of these that you make, you'll make 2 of them. So, sorry, 4 of them. And in this process, doing that citric acid cycle, which you see there, we can pull a lot of energy, a lot of electrons from this. So in this case, we have 6 NADHs. And then we have our 2 FADH. You can see as we're kind of walking through the reaction here, we're stealing electrons, and then stealing even more electrons, and you're building them up. So now the thing that we're gonna have to get into is, or dive deeper, is to look at how the oxidative phosphorylation works. How are we using all these electrons to actually make something happen? This thing has the nickname of, it's the electron transport chain, and it does chemiosmosis. So electron transport chain is because it's gonna use the electrons to mess with the chemical gradient, and then we're gonna use that chemical gradient to get energy out of the system. Alright. So, okay, so this is the simplified version of what's really going on. We're at the very edge of the inner wall of the mitochondria, right? So we kind of orient ourselves. Remember, mitochondria has a double layer. You have your kind of your outer layer, which is the one that's touching the cytoplasm. Then you have this intermembrane space, which is the dark orange section. And that's kind of what you're seeing back here, right? The intermembrane space. Then the little line, the junction between the yellow and the orange represents our inner mitochondrial membranes, which is this thing. And on the inside, you're looking at the matrix. So at the very, very core of your mitochondria, it's the matrix. Then you have your inner membrane. Then you have the inner membrane space. And then you have your outer membrane, which is the one that touches the cytoplasm. So when we're working with all these NADHs and PDHs, this is where we're really going to be doing a lot of the work. And it's going to be carried by these multiple little protein complexes. So just 1, 2, 3, and 4. There's 2 little intermediates, this Q and CT. And that's going to help us. Again, we're going to use up our electrons to power our reaction to build up the hydrogen ions. Right? So it starts on this side. Here's our NADH. It's going to go to that first complex. And again, there, the NADH is going to drop off. It's 2 electrons. It's going to let go of the hydrogen. But those electrons are what's going to help us kind of power this reaction up. And as we're doing that, we're actually pumping hydrogen ions into that intermembrane space. So that orange section is going to be super enriched with hydrogen. So in this case, we can pull out hydrogen from this step. This will kind of go through this Q complex, just the Q for now. If we keep following this pathway, we see that at the next step, once we hit our third complex, we have another event of these electrons are further helping us power up the reaction of we're kicking it out more hydrogens into that space. Right? This is a high concentration of hydrogen in that area, so you can imagine we're going against the gradient, so we need power to get that reaction to move forward. The electrons get transferred to the cytochrome C. These transfer them again to the fourth subunit. And then this one still does it one more time. It's going to be using that electron to carry hydrogen, kicks it out. The other thing is that at this point, remember your electrons out here started like this. Your carbon had balanced electrons, or equally shared electrons like that. In that case, this would be considered a super high energy molecule. So you have a lot of power in the battery. Once you get all the way to here, this is going to be our final electron acceptor. It's because your oxygen, I'm sorry, let's see those layers. Because the oxygen is gonna be holding on to them, this is technically our low energy state. So we brought in these bonds, super high energy inside of them, and the last thing that we're gonna end up hooking this up to is gonna be the oxygen. And that's gonna basically get turned into water, and now we've made our low energy product. So across these steps, 1, 3, and 4, our NADH has been giving out hydrogen ions. And then remember I was telling you guys earlier that FADH is lower energy relative to NADH. And the reason for that is that our NADH is able to bind to our first complex to help us pump out hydrogen ions. But if you look at the FADH, this protein is basically only sitting on one side. So it doesn't have any movement of hydrogen. So if you're kind of doing like really simple math, it's like with our FADH, we're only going to have 2 events to pump out hydrogen. With our NADH, we're going to have 3 events, right? 1, 2, and 3. So that's why NADH is more powerful and FADH is a little bit less. Does that make sense? Yeah.
So is the direction of NADH and hydrogen are opposite?
Say it again.
The direction of where the hydrogen is going is opposite to where NADH is going?
So sorry, NADH in its compartment. So inside the matrix, it's going to basically stay in that same compartment. What it's doing is it's transferring the electrons to this complex, and then the complex end is the one that's helping move the hydrogen. But it doesn't directly have to be the same hydrogen that you see here. This one, it's just basically there's a pool of hydrogen in the cell, and that's what you're kind of looking at. Is that gonna answer your question? Yeah. So yeah, so out of these NADHs, we've now turned what came out as the key thing to care about here is just electrons. This was the things that were temporarily holding our energy, and then now you've switched over to you've used these electrons, and now you've basically set up a hydrogen gradient, right? Something like that. On the outer thing, you had a lot of hydrogen. This thing now has the through osmosis has a huge driving force. So it wants to get back into the inside of the mitochondria. Yeah. So now we get kind of like that electrochemical energy, right? We're building that up. And that's where this pump is one of my favorites. It's called an ATP synthase, and it looks super cool. There's kind of 2 parts to it that we care about. You have this one that's kind of sitting on the membrane, in which case it has this kind of like little channels where the hydrogen ion can flow, can gradually go through them. But as it's going through them, it ends up making this thing kind of turn in place like that. Right? So the hydrogen ions are being used for their pressure to turn this molecule. As it's turning around, it's linked up to this part that's on the inside, right? Closer to the mitochondrial matrix, which would be this part. And in which case, this is able to grab an ADP and a phosphate group. And through that, like the hydrogen ions are twisting this thing at the top. Imagine it was my hands. The hydrogen ions twist this. And because of that, my feet spin. And then my feet basically kick together the phosphate onto that ADP. And then we can make that high energy molecule ATP. The engineering on that thing is beautiful. Like we'll have a video, I think, on this one, on the next one, where I can show you how it looks. And it's super awesome because it's literally made to perfectly catch the hydrogens. It twists as it lets them through. And this thing is like perfect pockets of it. It makes this now favorable, right? Because normally ADP, this is our low energy molecule. ATP is our high energy. It's hard to get these to glue, but this thing is perfectly grabbing them, snapping them together. At which point you pulled out. You're going to use your electrochemical potential, and then you got into the final step, right? Which is ATP, right? So then everyone's like, oh yeah, mitochondria, powerhouse of the cell, and they just tell you about this, right? It's like, hey, mitochondria makes all the ATP. But you can see we're gonna kind of have to go through different pathways to get ourselves to that big, the big product all the way at the end. Yeah, so glucose, NADHs are your electrons, your electron transport chain makes our hydrogens. Our hydrogens do this proton motor force, and that hydrogen ions are being the thing that's gonna finally give us the ATP. We're pretty good. Yeah, any questions on this one? I'd love to put it on the test on this. Let me see. Let me go back a little bit. All right, so here in this diagram, I like it because I want you guys to remember the position of stuff, right? Which is, the key ones are complex 1, 3, and 4. Those are gonna help us pump hydrogen ions, which is cases where we can build up this powerhouse, right? Our huge proton motor force. On the other side of that is the slight difference between these two. I love to bring these up, right? Your first complex can take NADH, gives us one extra and pumping out hydrogen. Our second complex recognizes FADH, and this one's only able to do the second two. So it's gonna be missing, it's gonna have a third S relative to the first one. So this is a lot of position information. On this next one, instead of looking at instead of looking at where they are on the membrane, here we've kind of reorganized them in terms of kind of like the energy that we have kind of coming into the system, right? So if you're looking at these are your complexes 1 through 4, right? And what we're doing is your NADH, that's gonna be our electron donor. So that's why, remember I was saying the terminology, right? If it's the electron donor, it's called a reducing agent. Here it's electron acceptor, so that's an oxidizing agent. So we're gonna have an NADH. When it transfers the electrons to your first complex, you can see we're sitting super high on this chart, right? Because this is our electrons are coming in super high power. Once it goes into the complex, it's gonna drop off some of that power in those electrons. So the little bit of electron power that we lost from this is gonna start getting turned into this energy, right? As we keep going forward, there's Q, there's the third complex, and here there's gonna be smaller proteins on the inside, and the electron basically gets passed down these. I'm not gonna have you guys memorize this. I do expect you guys to know these. So we go from 1 through Q, it goes to 3, we go to cytochrome C, and then we end up at 4. But each one of these events, when we're passing it down, we're getting it from a state where the electron is at a high energy state. Through that interaction, it does a little bit of work, and then we drop some of the energy of that electron. And we proceed through this pathway of keep ourselves going forward, putting out the energy that we need, till we get here to the last part, which is once you've taken everything out of that electron, like all the charge that it has, the cool, like the power, at which point your last electron acceptor is going to be your oxygen, right? You give this to the oxygen is going to be so negative, it's going to pull the electrons towards it like this. And now these things are going to be in this low energy state. So in this case, right, for us, we need oxygen in the system. This is why we have to, like, they call it respiration. We need it specifically for us to help us kind of catch this step at the end. If you don't give this thing oxygen, you basically freeze this whole thing up because there'll be electrons stuck there. And the ones on this side basically can't leave at that point. So you'll basically jam up the system. All right. This chart kind of makes sense to you guys a little bit? Yeah? All right. So I know it looks super complex in my notes. I would almost go back. You know, I would kind of cover up or like cross out a little bit this FMN, FESE, cytochrome, all these through the middle, and then all of these. I just want it to be 1Q3 4 or 2Q3 C4. Yeah. All right. So now we have position. We have the other one. And this is the one I was talking about, that little, for this guy, right? The last one where we're turning that hydrogen concentration into our actual ATP. These are the two components, right? This is the component that's kind of sitting on the plasma membrane itself. And here we're using the work from the hydrogen ions which want to flow in through this thing. And it's going to flow through these little channels and it gets popped in here. And as each one occupies it, it gives it the ability to kind of like a little crank set, which is like getting one step forward, one step forward. And as it's doing that process, you're bringing in hydrogens and you're dropping them off to the place where it's lower states. This is the one that is receiving the electrochemical potential and turning it into a mechanical aspect, right? Because now this thing is turning. And then on the inside, this is where we're using that turning to catch two of these lower energy molecules, your ADP and your phosphate group, and then you're basically jamming those together into each other to give this thing a charge. So, everyone feeling pretty good about this? Could you guys walk me all the way through it? Yeah, I know. All right, so let's go back. So I really want you guys to feel comfortable with this. All right, so in this case, you saw I was drawing it, kind of focused on the carbon side, right? Where we're saying, how do we get power out of the carbon? Again, start with our glycolysis. This little first box, that would be this one right here, right? Getting the stuff broken down. Your pyruvate processing, we're looking at this here, kind of going to there. And then your citric acid cycle is basically this step. If we're keeping track of carbons, that's the storyline. We get to CO2s, that thing's gone, right? On the other side is going to be this NADH, our electrons. Our electrons are being turned into our hydrogen concentration. The hydrogen is being turned into our ATP. So that's where I want you, I normally I kind of want to go over this one more time, just to make sure you guys feel comfortable with chasing the carbons down, the events where we pull out ATP, and then also chasing the electrons down, and then how we're going to pull the ATP. One thing I forgot to mention was, go back to the big drawing. Sorry, guys. Thought I had the numbers on here. So when it comes to harvesting energy, if the thing I would kind of want you guys to compare is if we're doing fermentation or respiration. Fermentation is kind of like what like yeast does. They eat sugar. If you leave them in the chamber without oxygen, they'll basically make a byproduct, which is alcohol. They're able just to work and get 2 ATP out of that molecule, right? Because they make it from the carbon, 6 carbon chain, they make 2, 3 carbons, and they're basically having. For respiration, we're able to kind of further walk ourselves down these steps. So in this case, we pull out a little bit, see 2 ATP and 2 ATP here. We basically pulled out a small fraction of what you can potentially get all the way over here. So again, this is another big indicator that our big powerhouse, the thing that really powers this thing up, is controlling those electrons and then kind of letting them go progressively to get the ATP energy out of it, right? So you can see 26 to 28 ATP, that's going to be a huge factor. And this is why, again, I was bringing up the whole importance of we need to be able to breathe because we need our O2s to catch these electrons. Get rid of them so we can get the circulation going. All right, let me see. So now that I've kind of walked through this little path, right, of how we can get our electrons out to this whole pathway of getting hydrogens, getting the ATP. If we go back to this chart, this kind of make a little bit more sense now, right? Where it's like, if the end product here for this first glycolysis is you're gonna retrieve about 2 ATP directly, right? You're gonna be able to cut when you break the sugars, you release 2 ATPs. That's a small unit of power. And you see the small little drop off, we're going from there to there, like, we've only stripped that much away from that sugar. If we looked at the NADHs, you can see that there's a way bigger drop off. And that means that when you do the split, technically this thing is taking most of the energy, right? And that's why you have these big jump drop offs. There's your NADHs, there's your NADH again, NADH. And again, we have 2, 4, 6, 8, 10 NADHs, right? And you have 2 FADs. So from that, you have what, 12 electron carriers, and then from 12 electron carriers, you're gonna pull out about 28 ATP. You can see we have a lot more efficiency at having electrons being carried there than we do of this pull energy directly just from ATP. But combining this two, this makes us super efficient. Give me a second. All right, so you guys have your notes, and hopefully some of you might have worked on this chart over the weekend, yeah? But now we're gonna try an activity where I'll be your artist, but you guys as a class gotta tell me what I have to care about as we walk through this thing, right? So we're gonna draw this together as a class, but I need everyone to kind of put it in the, make sense? So before we start, any questions? No, all right, let's go. All right, so we're starting with our glucose, right? On this side. So what's the stuff that I need to bring in to make sure we have this reaction happen?
Oxygen.
Yeah, so let's put in stuff. We'll make a list, you're gonna have to break up where, when you need it, right? But yes, you need oxygen, what else do you need? Oxidized, right? What's the stuff that, if we think about long-term, this is gonna be the things we're gonna use throughout. When you get all the way to the other side, what's the stuff that we're gonna finally be our products, stuff that we're kind of throwing away?
CO2.
Mhm. What else?
Water.
What else?
ATP.
All right, so this is the big thing that we're gonna start out with, and this is what we're gonna end with. If I talked about kind of everything that in the system is kind of cyclical, right? Like the plants make the sugar, we eat the sugar, and we send it right back, right? In which case, if we care about what's inside of these, glucose, right? Initially, it has the electrons, and it has the carbons, right? Those are the two molecules that we care about. As we're going into this process, now we have the carbon is gonna be here. Right, and then we're gonna get our electrons are basically gonna be being sent here. Right, so 6 carbons, they go from being together to individual ones. And then, like we said, our final electron acceptor is gonna be this oxygen, which is gonna be the one that's gonna make water for us, right? Yes, there's technically electrons here, but it'll be this oxygen are kind of more greedy than the carbon, where it almost feels like it doesn't have that much of a charge. So that's gonna be our big jump. All right. All right, so that's big picture, all the way at the beginning, all the way at the end. Now, let's go back and we'll say exactly what's going in, what's going out into each one of these basic steps, right? So we put, so say glycolysis, here's our first step. I'm gonna draw an arrow kind of down like that. And this will represent what's the stuff that we have to bring in versus the things that we're gonna send out, right? And then for the next one, I'll just kind of move it up and then we'll kind of go forward. For glycolysis, what's the stuff they're gonna bring into this guy? Just for this step, the one that are critical at this step.
Oh, that's.
What we're bringing. Like this section right here, somebody did it again.
Oxygen.
Say it again.
Oxygen.
It's not super critical at this step, because remember glycolysis, you can do it through fermentation and you can do it with respiration. So not yet, but eventually.
So is this not glycolysis?
This is the whole step. That's why I was kind of like, oh, this is big picture stuff. You literally went from here, you guys jumped all the way to this point. Right? Like, if we're looking at the electron transport chain, right? The stuff we just covered, the new stuff we covered today, we're basically on this side all the way over here. Right? At that point, this is the acid cycle. And then we have the electron transport chain. In this case, when we do this arrow like that, right? This is where, if we brought in oxygen, this is where one of the things we talk about, right? You actually, the O2 kicks in right here, and then our final product is our H2O. So it's like, in these other steps, we aren't technically using this thing at all, right? It's just, you're cutting CO2s, and then you're basically re-gluing, breaking water, gluing them to the carbon to make these guys. But you don't need to have an O2 present to actually help you make this reaction happen. Yeah? All right, so going back, glycolysis, just the sugar steps. You guys want to go up on the slides for this one, right? What are we bringing in?
Glucose.
Yeah, so this is where we are bringing our glucose. All right. Okay, what's gonna happen to that glucose now? On this side, let me pick on this side one more time. What's gonna happen to that glucose? Correct, right? So what is it? So if I call this a 6-carbon ring, what are we making?
2 carbons.
Yeah. So 2. That'll be our kind of our product, right? This came in, our 6, he broke it down into these 2 different sets. Okay, we'll go through this twice. Right now, let's keep track of these carbons, right? So you've made your 2-pyruvate. Again, this gets moved up, and it's part of the next reaction, right? So glucose went in, pyruvate came out. Pyruvate is the thing that's now going to come into the next reaction. What's the thing that's coming out of that one?
Two carbons.
Yeah, sorry. CO2. That's one of the things that's coming out. What else?
And two carbon rings.
Yep. What do we call that one? It's acetyl-CoA, right? CoA. And so these are 2 carbon rings. So then 3 carbons, you split it up, 2 carbons, and then one of the CO2s. All right, citric acid cycle. This edge over here, help me out, guys. Here we go. So we're keeping track of the acetyl-CoA. We're bringing it in. What's happening to that as we go through the citric acid cycle?
CO2
CO2 what?
is released.
CO2 is released, yeah. How many CO2s? So, because you have two carbon chains, the end product is you're gonna put out a total of 4 CO2s. All right, cool. So, carbon wise, we've kind of walked through this thing, right? All right. Now, let's reset this thing one more time. And this time in red, we're gonna be kind of keeping track of our electrons. So initially, you have your 6 carbon chain, right? The 6 carbon chain, kind of like I put in that drawing over there, it's carrying your carbons, but it's also the thing carrying all the high-powered electrons, right? It has the CH bonds, CC bonds. So when we go through that first step of glycolysis, what's gonna be the output electron-wise?
2 NADH are released. 2 NADH molecules are released.
Right, so then our output for here is gonna be 2 NADH, right? So that's gonna be our first, we got electrons out of this. For the pyruvate,
2 NADH.
two. All right, this corner, what's happening for the citric acid cycle? How much are we putting out there? What's our output?
Six NADH.
And what else?
FT.
So you can see we've been building this up. There's our NADH, a little bit more, and then we're getting a lot more. And then for the FADH, we finally get a little bit here, all the way at the end. And that's how we pulled out the electrons. Technically, they were still hidden. Like in here, the electrons were stuck inside the glucose. We stole 4 of them when we did this reaction, right? As you go through this process of we're breaking these 3 carbon chain, 2 carbon chain, this pyruvate, if I threw it up here, it again will have these extra 4 electrons, which are the ones that we steal, and 4 electrons, and we dump them into these 2 NADHs. And then in the citric acid cycle, we're doing the final thing of breaking this thing all the way through. You can see we can put out 6 NADHs from there and 2 other FDHs, which is we take the last little bit of these high energy electrons and we kind of basically breaking these out. 3, 6, 7, yeah, 14. One more. Yeah, one more. Right. That's what we're putting up a lot of the electron power, and we're going to put it into those NADH to carry it away. All right. Let me see. I'm going to pick on that back corner now. All right. So, at which point, let's go and let's shift our focus into the ETC, right? So the electron transport chain. So, what are we bringing in for that?
Oxygen.
Oxygen, yeah. So it's going to be our electron acceptor, right? It doesn't have electrons that are high energy. At the end, it's going to take the spent electrons here. So you can imagine it's going to take those like that because it's 2 on this side. Right? It's going to take electrons. Yes. What else? Yeah. Anybody on that side? That's usually.
Yeah, the NADHs.
What are they doing? In or out?
They're going in, they're bringing electrons.
Right. Right. I want you to be thinking that thing's going to be the carrier. It's bringing in NADHs. What's next? Unless you hate it. Sorry.
Also the FADH.
Also the FADH. Again, these electrons are basically coming in through the molecules, we put them into the chain. So we go through stuff, what are we getting on the other side? What's some of the products we're gonna get from this?
ATP.
Yes, but let's stay on this part before we jump there. Yeah, here we go.
The water is.
Yep, water's gonna be one of the other ones, but so what happens to these?
The hydrogen.
Yep, you're gonna make hydrogen ions, what else?
Do they get reduced?
How?
They lose an electron.
Say again?
They donate electrons.
So then what do I have?
NAD plus, FAD plus.
Right, so then now you have your electron carriers not carrying an electron. And that's kind of what we're keeping track here, right? You have electron carriers with an electron, and once it goes through this process, you're gonna split them up. Get your electron carriers back to their unbound state. And then over here, you can see our electrons are basically trapped inside of this. The power from those electrons, though, is gonna be inside of this part, which would be your ATP. We'll draw a little tangent here. A little more details, right? So in this case, imagine this one to be our NADH, and this is our FADH. Again, these are the two things we can send into the electron transport chain. This one uses complex 1, 3, and 4. Right. So from here, we get hydrogen concentration, hydrogen concentration, hydrogen concentration. Our FADH, remember, goes to 2, 3, and 4. And because of that, we only get 2 hydrogens relative to the NADH, we can get 3 back into this side. Yeah. So yes, this answer is correct, like we're going from here to here. It's just these two will be doing different levels of contribution to this. Right? So NADH will be doing 30% more than the FADH. Does that make sense? Yeah. I know it's a lot to keep track of. And that's why I was hoping today we go slower, we can go through stuff about how the carbon is behaving, how the electrons are behaving. But I highly suggest you have to look into this thing and feel comfortable with it. Right? I like to throw out questions or stuff for you guys to know what carbon you expect to go into a process, what to come out. I also expect you guys to keep track of the electrons. And then of course, I want the ATP values coming out of this. For the hard questions, I like to ask stuff like messing around with these. So let's say like, I'm like, hey, what would happen if technically your NADH aren't working? And all you're doing is you're putting all your energy to FADH, what would you expect from the system? Like for your ATP output?
There will be 2 less ATP output. 2 less ATP.
A lot less ATP, right? Because it's like, if you don't have these, you're not putting out the best, what's the best one, giving you a lot more hydrogens into the system. You only have this one doing the work, which is doing 2-thirds go down. And because of that, right, less hydrogen ions, weaker gradient means less time you can spin the ATP pump. Let me write this up. And I think I'm gonna make this a homework assignment. I'll give it to you guys and then try to see if you guys give me notes on it by Friday. Yeah. if you're unsure, or if you're like, hey, you know, something seems a little confusing, something that happens to me where I forget, like, oh, what happened in this step or that step? Try to use your notes to go back and be like, build your map like this from your notes, like from the slides, and put them together. If you're still having trouble, or even if you're like, hey, I just want to go talk to me, I'll be in my office hours. You guys saw it now, you can just click on that bright space thing and it sends you to reserve time. Reserve some time, come in and we can talk through whatever part you want. Yeah, but I really recommend you guys look at this. I'd love to talk about it. I'd love to put it on the quiz. And there's a lot, so I think it's hard to cram. So it's like we need to practice this more than a few times to get this thing to stick. Yeah? All right, cool. So let's call it for today. Sorry, if you guys don't have more questions, Al?
Yeah, well, I was. I'm sick in spring. I'll be so embarrassed. It's embarrassing.
I was wondering, oh my god.
Yes.
Yeah.
They're both awesome. I've
That's
heard,
what I've heard.
everything's super great about her. This guy is like one of my BFFs. So
Okay.
like,
Perfect, I signed up for that one, PFS.
and then it's not even a BFF qualification. I'm just letting you know that I'm a little biased, but
Yeah.
he did,
I've heard he's good.
he used to teach anatomy at Vanderbilt from there.
Oh,
So
okay,
it's-
awesome.
I'm like, I'm not sure about Sue. I know she's been great. She's done a lot of stuff, but he's a badass. I had him share slides with me for other classes. His slides are beautiful, like.
Perfect. Okay, and
he's
I'm
good
gonna
at his
stay in
notes,
that one.
And he's a fucking artist. Like, if you look at his stuff, you're like, you know, like crappy drawings. He has them nicely drawn in his stuff.
Oh,
Like, I don't know. He's an artist. That's all I'm saying.
Cool.
You're gonna love it.
awesome.
Yeah,
Thank you.
no problem.
I have a question. So